Hello, ST314. Katie Jager here, your instructor for the summer. I've decided to make a recording of this week's notes, especially for some of those that I've requested some more auditory type lessons. And so hopefully this will be helpful for the majority of you. Okay, so let's get started. This week we are looking at hypothesis tests for 1 and 2 population proportions. This corresponds with the sections 4.4 and 4.7 in the required textbook. Okay, so if we want to make inference for a single proportion, this is very similar to being able to estimate a population mean through X bar. And so last week we looked at the one sample t-test and also the one sample z-test to be able to test a population mean. This week we want to look at testing a population proportion. And so we can do that with this estimator p-hat. Okay, and so in statistics sometimes we simply just put a hat on our estimators to distinguish them from our then population parameter. Okay, so what is p-hat? P-hat is just basically the number of instances in which some event occurs, or it can be thought of the sum of successes. So it's just the number of times something happens, all divided by the sample size. So it's our sample proportion of the thing that we're interested in testing. Okay, so recall from week 3 when we did the normal approximation to the binomial distribution. So basically, there's some things that we need to check before we can then use this normal approximation. And those things are that your n times p naught is greater than or equal to 5, and n times 1 minus p naught, so the complement, is greater than or equal to 5 as well. Okay, well, what is this p naught? P naught is just our hypothesized population proportion. So it is the thing that we are claiming our population proportion to be. Okay, so if our sample size n times p naught is greater than 5, and if n times the complement is greater than 5, then we're good to go. We can perform a significance test for a population proportion using an approximate z statistic. Okay, so how would we do that? Let's explore an example. So in example 1 here, I have a potato chip producer has just received a truckload of potatoes from its main supplier. If the producer determines that more than 8% of the potatoes in the shipment have blemishes, the truck will be sent away to get another load from the supplier. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of those potatoes have blemishes. Carry out a significance test at the alpha equal to 0.10 significance level. What should the producer conclude? Okay, so how would we do this? First, we need to state the null and the alternative hypothesis. Basically, we want to perform a test at that 0.10 significance level. Okay, so what does that mean? That means that when we're through calculating the test statistic, that if our p-value is less than that significance level, then we can reject the null hypothesis. Okay, but let's not get ahead of ourselves. What is the null hypothesis? Well, here we're claiming that the proportion of potatoes that have blemishes is 0.08. Okay, now if that proportion is larger than that, then the truckload will be sent back of potatoes, remember. So the alternative then is a one-sided alternative where p is greater than 0.08. Typically, the alternative is what we are really interested in hypothesis testing, and the null is just simply a statement of no difference or just kind of a null statement. Okay, so P is the actual proportion of potatoes in this shipment with blemishes. In other words, this is our claimed population proportion, so 0.08. Okay, So remember, we have to check these conditions. If the conditions are met, we should do a one sample z-test for the population proportion P. Okay, first we need to know if this is a random sample. The supervisor took a random sample of 500 potatoes from the shipment, so we're good. Okay, is it normal? Okay, so this is that condition of n times p naught, so 500 times 0.08 is equal to 40, and n times 1 minus p naught is equal to 460. Okay, so both are greater than 5, it's safe to do the normal calculations. Okay. So now we need to state the statistic and calculate the p-value. Okay, the sample proportion of blemished potatoes is then just simply p hat, that's 47, that's the number of potatoes that had blemishes out of the 500 in the sample. Okay, so our p hat is 0.094. Alright, here's our test statistic. So z is equal to p hat minus p naught, all divided by the square root of then this variance, that is p naught times 1 minus p naught divided by n. Okay, and we can see here that I've inputted the values for our p hat, our p naught, our hypothesized value, and then this is our variance. We get a test statistic, so z-test statistic of 1.15. Okay, and we can now look this up either in a table, or we could use our calculator, or we could use software. Here I've looked it up in a table. So the p-value of obtaining this particular proportion, given the hypothesis is true, is 0.1251. So the probability of z being greater than or equal to 1.15 is equal to 1 minus 0.8749. This is the value that I got from the table, okay, and subtracted from 1 because I want the greater region is 0.1251. Okay, so that would be our p-value. So what can we conclude then from this test? Since our p-value of 0.1251 is greater than the chosen significance level of alpha equal to 0.10, we will fail to reject the null hypothesis. So there's not sufficient evidence to conclude that the shipment contains more than 8% blemished potatoes. The producer will use this truckload of potatoes to make potato chips. Okay. All right. Well, just like we did before when we were talking about the means, we can also do a confidence interval for the population proportions. And I think maybe on this slide it's cut off a little bit, but we'll specifically be able to show you an example here in just a moment. So a significance test is not the only way to test or describe a population parameter. We have to remember that we can always do a confidence interval as well. And so we can do this with the same format, estimate plus or minus the critical value times the standard error. All confidence intervals will have the same type of format. Okay, so in this second example, we still have the potato chip producer, and so a potato chip producer has just received a truckload of potatoes from its main supplier. The producer would like to estimate the proportion of potatoes with blemishes. A supervisor selects a random sample of 500 potatoes from the truck. An inspection reveals that 47 of the potatoes have blemishes. Calculate the estimate for the proportion of blemishes and include a 90% confidence interval. Okay. So how are we going to do this 90% confidence interval? Pretty straightforward. It's simply just plugging in some values. So the estimate for the proportion of blemishes, again, was 47 out of 500 potatoes had the blemishes. So our sample proportion, p hat, is 0.094. Here we can simply use this calculation to do a upper and lower bound. Okay. So 0.094 plus or minus my critical value. This is z alpha over 2, so I got this from the z table, okay, times 0.094 times 0.906, this is simply just the complements of each other, so this 1 minus p hat, all divided by then the sample size of 500. So this is my standard error, this is my critical value, and this is my estimate. Okay, so finally then, I find that the true population proportion of potatoes with blemishes is estimated to be 0.094 with a 90% confidence interval of 0.073 to 0.115. Okay, so recall that we weren't able to reject our null hypothesis in the original hypothesis test. Here we can also conclude that with this particular confidence interval. But there's one thing here. Okay, our test on whether the population proportion was equal to 0.08 was not rejected at the 0.1 significance level. We can confirm this with 1 minus 0.1 times 100% confidence interval. Given the hypothesis value, 0.08 falls within the interval of the true possible population proportion. So since 0.08 fell within this interval, then we were able to also fail to reject the null hypothesis because it's within that particular interval, that 0.08. Okay, so here I've suggested some exercise for you. Go ahead and do some practice, and these are then some solutions for you to check your answers. Okay, now we can do inference for two proportions. Suppose we want to compare the proportions of two independent populations. Again, we can estimate each proportion by taking a random sample from each population. Okay, so we can estimate these things same like p hat before, but now we have p hat 1, first population, and p hat 2, the second population. Here our population distribution, we believe for P1 hat minus P2 hat is normally distributed. Okay, and this picture just depicts that with a standard deviation here above and a mean of our true population differences of P1 minus P2. Okay, so here's another example. A manufacturing company produces water filters for home refrigerators. They have some quality problems with leaks. Out of 300 filters, 15 of them leaked. A project used a designed experiment to improve their quality after the treatment from the experiment. A sample of 300 filters yielded 7 leaks. Is there evidence that the treatment improved the quality of the filters? Perform a significance test to compare the original population proportion of leaks and the treated population proportion of leaks, significance level 0.10. Okay, so how would we go about this? Well, first we need to state the null and alternative hypotheses. Basically, we want to perform a test at the alpha 0.10 significance level. Here, this is my null. I have my original population proportion minus the treated population proportion, and then if the treatment reduces the proportion of the leaks, then the difference in proportions should be greater than 0. So that's my alternative. Okay, so we need to calculate the test statistic. Here, in the test statistic, we use a pooled estimate for our variance. So our numerator has the difference in the proportions. Then we use this pooled estimate. So y1 plus y2, all divided by n1 plus n2. Next, we get then a test statistic of p or z greater than or equal to 3.50 is equal to 1 minus the probability of z less than 3.50, and we get a p-value of 0.002. Okay, so again, your text typically looks at a critical region. Here the critical value for z is simply just 1.28. Our test statistic exceeds 3.50, and so therefore we would reject the null. Okay, we already knew this from our very small p-value, but the p-value is just so much more informative than the critical region approach, and therefore I prefer it. Here are the calculations then for that particular test statistic. Okay, what is our conclusion? There is convincing evidence that the treatment reduced the proportion of leaks among the filters. The null hypothesis of no difference between the population proportions is rejected with a p-value of 0.002. Okay, again we can do a confidence interval for the difference in proportions. Here's the formula, the general formula for the confidence interval of the estimate, and here's an example. So we go back to the same manufacturing example. Here we want to do a confidence interval of the difference between these two refrigerator filters. Okay, so what is the 90% confidence interval for the difference of the two population proportions? We can input the values into the formula and we get this estimate. The estimate for the difference in proportion of leaks between the original population and the treated population is 0.027 with a 90% confidence interval of 0.001 to 0.052, meaning the treatment population has estimated 0.1% to 5.2% fewer leaks than the original refrigerator filters. Seems as though the treatment helped reduce the leakage.